Hello and welcome on
Hello.
stage.
Thank you for having me.
Lovely to have you. And Beth is going to tell us about additive manufacturing of electronics for, guess what, space applications. So it's perfect. So the stage is yours and good luck.
All right, thanks so much for having me. So I'm Beth Paquette. I'm from NASA Goddard Space Flight Center, which is actually just outside of Washington, D.C. And today I'm going to talk about some additive manufacturing that we're looking at for a couple space applications. Specifically, when I talk about additive manufacturing here, it's more of a hybrid approach. So we call it printed hybrid electronics. So we use additive manufacturing techniques where we start with an existing substrate and then we deposit conductive and insulative materials to build up a circuit, and also using existing electrical components. So it's not fully additive process at this point, so we call it hybrid. But why do we like this? Why are we interested in this approach? Because there's the advantage of fine feature sizes. We've seen down to 20 to 30 micron trace widths in our labs, and vendors have also claimed, 10 microns is also possible. And you can print on a variety of substrates. You're not limited to thinking in circuits that are just two-dimensional. So non-planar surfaces, domes, around bends, and things like that. So that helps us with our, size, weight, and power. When you go further out into space, you have limited amount of things that you can take with you, constrained resources. So saving on space is important. So I'll go over a couple examples of applications where this may benefit us. First, I'm going to go over the Hard Energy X-ray Photoelectric Polarimeter, HXPP for short. This is an application that where we're looking at sources of X-rays out in space. So, black holes, quasars, things like that. Anything that emits an X-ray, we'll be able to look at that and find out more about it. So how does this instrument work? So we have an X-ray beam that comes into a gas chamber. It creates photons in the chamber, and then those photons are read on these strips. The strips are, they consist of about 100 or so parallel lines, about 120 microns spacing on those. This is typically made with a liquid crystal polymer that has copper cladding on it, and it's etched away to create this pattern. Then the LCP gets bent around this 90-degree bend and wire bonded to a rigid ASIC readout board. And then there's a series of these together because while we'd like to make one long strip, there's a capacitance buildup. So we really need this 90-degree bend to put in these ASIC boards and have them in series to collect the data. Now, when you're working with liquid crystal polymer, it's very flimsy and thin. I always describe it like you're working with a grocery bag. It's very flimsy, and it's easy to crinkle, and it's easy to tear. So if you get any crinkles or tears, you pretty much have to start the process over. And the process of putting it on this frame and bending it, and then also having to bake it out to keep it really clean, it's a lengthy process. So this is one application where we see a possible benefit of using additive manufacturing. So instead of the liquid crystal polymer, flimsy, flexible material, we've looked at using a rigid substrate instead and printing those traces around this 90-degree bend. So here we looked at a Maycore substrate and using commercially available silver inks to print this pattern with aerosol jet. We've seen consistent width